Let's look at the limit in problem B. I want to evaluate the limit as x approaches 3 of this rational function. I know that when I do direct substitution, I'm going to get a finite value in the numerator. I'll get 2 minus 15 or negative 13 over 0. When you are evaluating a limit and you get a finite value over 0, we said there are 3 possible answers. Either infinity, negative infinity, or does not exist. Every single time you get a constant over 0, your answer is going to be one of these 3. Our job is to set up a sign test, set up the intervals, and so we first want to find out where the numerator is equal to 0, and also we already know where the denominator is equal to 0. So when I'm setting up my sign chart, I know I'm going to have at least, that's where the denominator equals 0. The numerator equals 0 when 2 minus 5x equals 0, or when x equals 2/5 when you solve that. Again, the reason why we find out where the numerator is equal to 0 is because between any two zeros and or vertical asymptotes, a function is either completely above or completely below the x-axis. If I pick one test value and it's positive, I know in that region the graph is completely above. If I pick a test value and I get a negative value, I know that the graph would be completely below. So I'm going to put 2/5 right here. And so I want to test, it's a two-sided limit that I'm trying to evaluate. I want to find the left-hand limit, and I want to evaluate the right-hand limit. So I need to pick a test value to the left of 3, and that value has to be between 2/5 and 3, and so I can choose 1 or 2. Either one would work. I'll choose 2. I pick a value to the right of 3, which would be 4, and I test these to see the sign of the function. And so when I evaluate by substituting a 2 in, again, I just care about the sign. So 2 minus 5 times 2, that's going to be a negative number in the numerator. And then 2 minus 3 squared is going to give me a positive number in the denominator. And a negative divided by a positive is a negative. So I know that all values will be negative in here. So the function is approaching negative infinity as x approaches 3 from the left. Now let's test 4. When I substitute 4 in the numerator and in for the denominator, in the numerator I would get 2 minus 20, which is a negative number, and 4 minus 3 is 1 squared, which is positive, and so a negative divided by a positive is a negative. So my right-hand limit is also negative infinity. So this means that my two-sided limit, even though it doesn't exist, it can be described, and it will be negative infinity. Alright, so in the first scenario, we knew we had a constant divided by 0, and we knew that there were 3 possible answers: infinity, negative infinity, and does not exist. We found out where the numerator and where the denominator is equal to 0, so we could find the endpoints of our intervals. We really cared only what was happening to the left and to the right of 0, which is the value our x is approaching. Since the one-sided limits didn't equal each other, the limit didn't exist. In the second scenario, the one-sided are the same, and so the limit is equal to negative infinity. Again, undefined, but the behavior can be described. So at this point, I'd like you to pause the video and evaluate the following limits, and start the video again when you've completed them. And again, if the limit is a finite value, if you actually get a value, that is your limit, and you can stop. If you get a finite value over 0, then you have to decide, is your answer positive infinity, negative infinity, or does not exist? number 1, the limit as x approaches 2 of x times x minus 1 divided by x minus 2. We'll start using direct substitution, evaluating the function at 2. 2 times 1 gives us 2 in the numerator, and 2 minus 2 we get 0 in the denominator. We have 3 options for our answers. The answer is either infinity, negative infinity, or does not exist because we have a finite value in the numerator and 0 in the denominator. We set or draw a chart so we can test the signs. We find out where the denominator is equal to 0, and that is when x equals 2. The numerator equals 0 when x equals 0, and when x equals 1. So you can see how important it is to check and find out when the numerator is equal to 0 also, because now we've broken up this function into 4 different regions, and only 2 of them do we care about. And so if I had ignored that step, I may have used 1 as a test value and it wouldn't have worked. So now I'm going to choose a test value to the right and to the left of 2. So to the left of 2 I would use 1.5, or any value that's between 1 and 2. To the right of 2 I'm going to choose 3. When I substitute these values into the function, I'm going to have 1.5 times 1.5 minus 1 over 1.5 minus 2. Again, all we care about are the signs, and so in the numerator I have a positive times a positive, which is a positive. In the denominator I have 1.5 minus 2, which is a negative. So a positive divided by a negative is equal to negative. And so I know that the limit as x approaches 2 from the left is negative. So that'll be negative infinity. I choose my test value 3. When I substitute that into the original, we get, in the numerator, we get 3 times 3 minus 1, which is a positive, and in the denominator, 3 minus 2 is 1, which is also positive. So a positive divided by a positive is a positive. So the limit as x approaches 2 from the right is positive infinity. And since the one-sided limits don't equal each other, then we would just state that the limit does not exist, meaning not only does it not exist, we can't describe it. Let's look at problem number 2. We'll start with direct substitution. Direct substitution leaves us with 0 over 0, so we know we have to do more work. This is a rational function, so we'll factor. The x minus 1's will cancel. When I substitute 1 in for x, I get a value of 2. Practice problem 3. Direct substitution results in 1 over 0. Set up my sign chart. I know the denominator is equal to 0 when x equals 4, and the numerator is equal to 0 when x equals 3. I'm testing, I only want to find the limit as x approaches 4 from the left, so I really only need a test point in the region to the left. And again, it was a good thing that I tested, otherwise I may have used 3 as a test value. That's an end point, so I'm going to use 3.5. When I substitute my test value of 3.5 into the original, I just care about the sign. 3.5 minus 3 is positive. 3.5 minus 4 is negative. So I'm going to have negative infinity as my one-sided limit. There's no need to test the right-hand side because we only want to find out what's going on from the left. The last one, number 4, the limit as x approaches pi from the right of the cosecant. So when I do a direct substitution, I get the cosecant of pi That's equal to 1 over the sine of pi, which gives you 1 over 0. So this is a one-sided limit. When it's a one-sided limit, I know the answer is either going to be positive infinity or negative infinity. And to do this one, I'm going to graph the cosecant function. And that's why I asked you and had you learn those graphs at the beginning of the semester, to make these limits a little bit easier for you when you don't have a calculator. Remember, when graphing a cosecant function, we can graph lightly a sine function. Sine has zeros at the beginning, half of the period at the end. It has a max a quarter of the way and a min 3/4 of the way. And that would have been your sine function. Since the reciprocal of cosecant is the sine, or the reciprocal of the sine function is cosecant, when I take the reciprocal of 0, I'm going to get something that's undefined. I'm going to get a vertical asymptote. So anywhere the sine function is 0, the cosecant function will have a vertical asymptote. So I'll draw those in. And even though the vertical asymptote at pi is really the only one I need, just to complete one cycle of cosecant, I'll fill those in. The reciprocal of 1 is 1. So we'll have the cosecant and sine graphs share this point. From here, you would just invert the U shape and let your x, as x approaches pi from the right, the y values are going to go to negative infinity. So the limit is equal to negative infinity. Now, if we did not include the plus sign here, in other words, we had a two-sided limit, not a one-sided limit, then the limit wouldn't exist. The limit as x approaches pi does not exist because you can't describe it. So as you approach from the left, your y values are going to infinity, and as you approach from the right, you're going to negative infinity. So in the next video, we're going to just kind of summarize finding vertical asymptotes and holes in a graph and writing the equations and the ordered pairs of those.